Hello, I wanted to discuss definition and identification of coherent structures in turbulent flows. These are the structures that persist on time scales longer than the highest frequency small fluctuations in turbulent flows. And when we describe complex flows in fluids such as plasmas, typical turbulent flows in atmosphere, engineering systems, or astrophysical systems, the word filamentary comes up very often when we look at certain types of coherent structures within these flows. We say that things look filamentary, but we often actually lack precise definition about what it actually means, or even intuitive definition, although that seems to be available right away. It's a little bit elusive. So in this video, I wanted to explore the question using this image of the Elephant Trunk Nebula, but with the important constraint that we'll treat it as a purely scalar field, not an astrophysical object, just the distribution of the light intensity over two-dimensional domain. So this image can be treated as a scalar field, I of xy defined over a 2D domain, so the intensity of the light is a function of x and y, and essentially the brightness is the signal that we analyze, and the geometry emerges from how that value of brightness varies across the space. When we say something is filamentary, we are not identifying objects in the usual sense, but we are describing how structure is organized in that scalar field. What immediately stands out in this image is that the structure is not uniform. The gradients of light intensity are concentrated into narrow, elongated regions. So some areas are relatively smooth, while others carry very sharp transitions. This is a physical feature of nebula and turbulent flows as well, but just abstractly as a scalar field we can see this uneven distribution, which we refer to as intermittency, is a very important feature of flows that we are typically interested in. So intuitively we call these elongated connected regions filaments. They are long relative to their width, they persist across the space, and they form networks rather than isolated blobs. But this intuitive definition starts to break down relatively quickly if we start to vary parameters for producing this flow or scalar field representations. So, for example, some regions look filamentary only at certain zoom levels, and other regions fragment into smaller structures if we look more closely. Some filaments that feel obvious, they kind of fade into the background depending on the contrast changes. And so this is immediate problem. Our visual definition of filamentarity depends on scale, resolution, and presentation of the data. And this is the real difficulty, the foundation of the difficulty. If filamentarity is an intrinsic property of the field, and this is what we are trying to determine what it is, we would expect it to survive reasonable changes in how the field is actually obtained or represented. So in practice, though, smoothing can erase filaments, sharpening can invent or manifest filaments. So this is a very known photography feature. If you over-sharpen a photograph, you can create artifacts, the artificial filaments at the boundaries, for example. The downsampling can change connectivity of the filaments, and contrast stretching, which is very common in astrophotography, can exaggerate or suppress filaments depending on how it's implemented. So this all is also very familiar if you're working with turbulent flows. For example, in large eddy simulations, LES, scalar fields often appear highly filamentary, but the exact appearance of those filamentary structures depends strongly on grid resolution filtering and subgrid scale modeling. So extracting knowledge from kind of LES data, so the physical insight is not very easy, not obvious how to do it. So the question becomes, if a diagnostic only works at certain scale or at one contrast level, is it really a diagnostic way? Is it diagnosing the structure or not just our choices and how that structure, our scalar field, is represented? So instead of jumping immediately to specific tools for diagnosing or determining the coherent structures, it's more useful to ask what a good filament diagnostic tool should be able to survive. As a minimum, it should respond to a control way to filtering. It also should distinguish elongated structures from blobs or sheets, obviously. It should reflect local geometry rather than global appearance and remain meaningful across changes in resolution of the data. So whether we're talking about passive scalars in turbulence or gradients of vapor fraction in cavitating flows or some pressure-based scalars, the diagnostic should tell us something about organization and not just the representation of the scalar field. So that's why the identification tools need to be defined very carefully and then applied to controlled data sets at various resolutions, such as different grid resolutions of LES or different point spread function values for astrophysical data, and then compared for the persistence of the particular types of coherent structures in the flows. So this is what we are looking for and trying to develop this kind of techniques that hopefully will provide eventually insight into also the underlying physics for the actual appearance and generation of these structures in otherwise random and kind of very chaotic turbulent flows at the vast range of temporal and spatial scales.